All right, guys, let's get started. So in the first half, we went over the homework and features and everything. Now in the second half, right now, we are starting, now the focus will be more on machine learning. I will be spending some time on features. As I said, I'm going to, some of the examples now will involve, instead of text, they'll involve images or things like that. But I will be spending a little bit more focus, or the focus now is gonna move towards the machine learning. Now, so I have to give you a little bit of history on this. So, you know, there's a lot of libraries, first of all, as you have seen, right? But this is truly what we're doing right now is we're starting now machine learning with a focus on parallel computing and big data. So this is where now the GPU processors will become effective and useful to us, right? Because that's the focus, that now we can process big data. So we're lucky we have this Scholar cloud, and so we'll be using that as I did before. So there's a lot of libraries out there for big data. So now remember, this is not just machine learning anymore. This is now machine learning for big data, and in particular, deep learning. There's some great libraries out there. There's something called PyTorch. A lot of people like it. There's Cafe. There's, you know, you can always just write the code in CUDA-NN and you know, the CUDA library, they have their own version. So there's a lot of tools out there, right? The one that we're gonna use is Google's TensorFlow. Okay, so Google is always really, on top, ahead, as you might imagine, right? Ahead of the curve. And so I think they kind of set the pace, to be honest. There's some great institutes out there like Google Brain, Google AI, there's OpenAI. So those are all great organizations, and they all are involved in this. And so these libraries are basically, things that they have developed. So before 2015, TensorFlow was an in-house product or tool at Google, but they decided to make it available in 2015. So it's been around roughly right now 5 years, okay? And in those 5 years, they've made changes. So again, I go back to this idea, what is Python or a Python library? Remember that Python is nothing more than sort of an interface to C, C++. So ultimately, the libraries have binaries and executables that are C and C++, which means they're very fast. Because we are using GPUs, that means that we're using CUDA. And CUDA is the library created by NVIDIA to use GPU processors, which were initially made for computer graphics, so that they can be used for machine learning applications. All right. A little bit more of the math and all that, how it works, the linear algebra will be more emphasized in 530, in ITS 530, which is the deep learning algorithms class. In this one, again, we're taking a more of a top-down approach. So we really want to get started as quickly as possible doing, analyzing data and things like that. So that means, that used to mean using Keras alone. So now a little bit of the history of TensorFlow. So TensorFlow, as I said, in 2015, they came out with TensorFlow. They called it later TensorFlow 1, right? And TensorFlow 1 was really great. It was the low, especially in the low level API, it was very low level. So you really could do everything that, like if you were writing out the math, you could really do it like that. Some people didn't like that. Others love that. And there's been this huge fight between the ones that like the low-level API and those that like the high-level API. I believe personally that the low-level API grants you a greater understanding of deep learning algorithms. But other people will argue that the low-level API is easier to understand. So I forget his name, unfortunately, but a guy came up with Keras, which is a sort of a wrapper around, let's say, the low-level API of TensorFlow. And there was a lot of people, as people will do, tended towards Keras, right? And so, and the people at Google had to adapt. So plus, obviously when you have something that's the first iteration of something, it'll have bugs. There's certain things that people didn't like about how deep learning works and everything. In particular, TensorFlow. In particular, now we have to think of something called a computational graph. So right now I'm just kind of throwing words at you. Don't worry about it. So the computational graph is the thing that you still have to create that. It's just that now it's not so obvious, I guess. But the computational graph is what? As the name implies, it is a directed graph, as you might imagine, of nodes and circles, or nodes and links. And that is your program. So you have to build a program where data flows. How you have data sets, and the data sets flow through a graph, and sometimes the nodes are data and sometimes the nodes are operations, okay? But you used to have to do what is called a static graph, which means that you had to create the entire graph first. And then once you created the graph, and only after you've created every element of the graph, you would run it through something called a session, right? So that's the TensorFlow Low Level API. That's how TensorFlow works. And the reason for that is that because everything is sort of written in parallel and written in C, you have to kind of, in Python, create this graph by writing code. And then you have to basically compile the graph and run it in the background. That's the way it would work. Now, people didn't like that. I'm still going to cover that at some point, probably in 5:30, not in this class. I'm just really doing history right now. I'm not really explaining these. But I want to put it into context, all right? So over 5 years, people have given feedback, and the people at Google came up now with TensorFlow 2. So the graphs are now dynamic instead of being static, which means that, and basically the gist of it is this, that whereas before, whenever you were programming in TensorFlow 1, even though you were using Python, the style of programming that you were using was not very Python-y. It didn't really feel like Python. It was not intuitive, some people would argue. And so they changed that so that now TensorFlow is more consistent with the way that you normally program, which means it has to be a little bit more dynamic instead of being so static and then waiting to run at the end. And also, it's more like NumPy, it's more like sklearn. So they just made it more consistent. They also fixed the bugs, as I said, and the code is optimized. So they've added tricks in the code, in C code binaries in the background to make things faster, better. They've done a lot. So a lot of great things. But unfortunately, that creates yet another style of programming that we have to learn. It's not just all the programming that you knew and then how to write a computational graph. Now you have to understand the concept of a computational graph, but you also have to learn just some programming essentials before you get going with TensorFlow. That's really how I would describe it. Is just, so initially what we're going to be doing is we're going to be learning this new style of TensorFlow 2. You didn't have a chance to learn the TensorFlow 1 and then but that's fine. So it's, things change, right? TensorFlow 2 has some things that I'm actually not crazy about, and what makes me worried is that 3 years from now they're going to change it again, right? Because it's an evolving thing. So in this field, you have to be prepared to just stay up to date, okay? Things are gonna be changing constantly. And so because progress, it just moves so fast. It's actually a good thing in a way, right? Because things are really moving and progressing and amazing things are happening. And really the changes are there supposedly to make you better, more efficient. And yeah, I can definitely see the efficiencies of TensorFlow 2. It's got some nice things, and then it's got some workarounds that are a little bit odd. But okay, so one thing, like I said, in the past, historically, you had TensorFlow 1 and the Low Level API, but then somebody built Keras. And Keras was a wrapper around the Low Level API, which was a little bit more object oriented, and it was supposed to be a little bit more like intuitive in the Python environment. In TensorFlow 2, Keras is now basically a part of it. They've embraced it, the ideas, and they built TensorFlow kind of with Keras in it. So now you use Keras a lot more, and you kind of have to, okay? There is a little bit of abstraction going on in the algorithms. So if you really want to get all the details of the algorithms, you still need to go to the, but for our course, for 520, which is just a top-down approach, we really don't have to do that, all right? So anyway, that's a little bit of the context and the history of TensorFlow 2. Hopefully that makes sense. So what I'm gonna do now is, like I said, and I explain all of this because we're gonna just have to do some coding examples, okay? So that's really what we're gonna do in the next, today. So if you notice here, I have, you should be seeing hopefully the bright space. And I just clicked on TensorFlow 2, and if you click, I have a link, right? And you can see I have some Python examples here. So that's what I'm going to be going over today, just kind of giving you some examples. We're not gonna get to all of these today. I'm gonna start, I believe, with example.py, just to get a feel. Think of it that way. We're gonna get a feel for TensorFlow and kind of how things work. And then we're gonna make our way through TF2 examples. We're gonna use some images. So we're gonna learn about processing images. And then finally, we'll start with our very first machine learning algorithm, which is linear regression, all right? More of a coding approach. So we're gonna start, it's like we're very slowly getting into the water, right? That's kind of how TensorFlow 2 is. It kind of gets you in there slowly. All right, so, but anyway, we require a little bit of background for this, okay? I'm going to start talking about a lot of libraries. So if you'll notice, I'm gonna start introducing a lot of new concepts like NumPy, right? Even though I've moved NumPy and TensorFlow operations further down, because I think I don't really need to get to these right away. So we'll see if I need to, I'll jump into them. But I think what I have in my examples is good enough to get us started. So my suggestion for this, guys, this is not easier. This is not easier than what we've seen before. Okay, this is not sklearn. This is a step further. So, but what I want to convince you of is that this is power. Okay, this is serious firepower. This is the real thing that you would use in an organization. And with what we have with Scholar and the GPU boxes, and this, you really have something that is state of the art. But like I said, what we're going to do is just today, just get started a little bit with it. My suggestion to you is practice, practice, practice. So go home, do these again, make sure you understand them. Also remember, you have your book, the book that's for this class, the machine learning book. And I take a lot of these materials from the book. So it's already there. You can read, follow along with your reading assignments and everything. Okay? All right, so we're gonna get started in a second. So I'm just, I believe Mitch had just something really quick to say about the Scholar. Mitch, are you there?
Yeah, I am.
Okay, so you just said you had some update. So can you mention the video, or in case people missed it?
Yeah, there's I sent the video to everyone. That basically contains some of the updates, the new way how to use Scholar, I'll call it. So go ahead and you can give that a look. That should fix all the bugs we have currently going on.
Are we still connecting in the same way? Are we still connecting in the same?
Yep, the same link, same everything. It just changes once you get into it.
And then it was. Right, so it's this one, remote desktop. We're still using that.
Yep.
Yeah, guys. So just what I would suggest is follow along. We don't need the GPU boxes today. So remember that TensorFlow 2 will work with CPU or GPU. So you can in fact just install it on your laptop or Mac, Linux, and just try it out. Right? You can try it in Windows, Anaconda, and everything. Play with it. I'll just be using Scholar because I want us to get used to this resource. But for today, we don't really need the GPU boxes, so you can just, as part of your assignment, follow Mitch's video, right, and try to do the configuration that he's saying, so that we have a GPU working environment going for the future. Okay. Right, so I'm in the Scholar. And like I said, today we don't really need the GPU boxes, but just follow Mitch's video. Are there any questions, guys, before we have anything has been said?
Professor, something wrong with your sound. I don't know what you're saying.
Guys, you're having trouble hearing me?
Yeah, because it's just not clear and broken.
Yeah, you're a bit robotic.
Robotic? Really? I don't know. Still robotic?
Yeah.
Still the same though.
Okay.
Since you switch over to Mitch, I think that's where it went all like a static type.
Okay. Hear me better now or no?
No.
Still the same.
Okay, so I don't know. I guess I can.
It's better now.
It's better now.
Yep.
Okay, everyone hearing me better now?
Yeah.
Clear now. Yeah. I don't know. I'm just pressing buttons on Zoom, so it seems to be a Zoom issue. Okay, so I guess tell me if it's still bad at some point. If it comes back, if it gets bad again, and the only thing I can think of is restarting the Zoom. Okay. All right. So are you guys seeing currently the Scholar?
Yep.
Yes.
Okay, great. All right. So what we're gonna do is we're gonna start. So we have like a good hour. All right. So I'm gonna move through this. Like I said, the code is there already on GitHub. You can download it if you'd like and just read through. I'm gonna type it up. I like to do that. Helps me to make sure I covered everything. And as I said, we're just getting started into this. So the best way sometimes is just kind of jump into something. All right, so we're gonna play with it. So I'm just gonna go ahead and I'm going to navigate to ITS 520. All right, so you can see here I had some old files. All right, I'm going to go to that general examples link. And from there, if you notice, I have example.py, I have images.zip, I have Keras TF2 linear regression, and then I have TF2 examples. So I'm just going to start with the most basic one, which is example.py. We're going to start. There's a lot of new things in TensorFlow 2. We're going to start looking at them and kind of just making sure it runs. And then from there, kind of get a better feel for them. Okay, so I'm also going to look at the Conda environment list. Oh, bash. All right, and then I'm going to repeat. Or not. This is really slow today. All right, a new issue. Good. All right, so I'm going to start. I like to use this one, TF GPU. I'm going to activate. All right, and if I do, so now I'm just going, I'm in the environment, and now I'm just going to do, just going to test something. I'm going to do Python, and then I'm going to do TensorFlow. Oh, import, sorry. So it's definitely slow. I'm noticing that today's Scholar is a little bit unresponsive.
It's not just today. It's going on from the last 10 days.
Is it? It has been slower? Okay, I didn't know that.
It wouldn't even move.
I don't know. All right, so let's start now just looking, as I said, at practicing a few things. All right, so I'm gonna exit out of here now. And I'm going to create a new file. And I'm just gonna call it, nano. You can use gedit if you'd like. You can use any editor that you want. Let's say TF2 examples, or you can, you can sometimes change, make it examples.py TF2. Examples TF2.py. All right, so here is this. So now basically the first thing you have to do, just like we've done before with sklearn, I'm just going to import TensorFlow as TF. Okay, and I'm also usually you import NumPy. We're going to be using NumPy. NumPy now, one great thing about TensorFlow 2 is that NumPy now works seamlessly with TensorFlow 2. So basically, you can use NumPy arrays, and really easily fit them into your TensorFlow model. So that is actually a really good thing. So NumPy as NP. Okay. And I love to have this print statement at the end just to make sure everything is running. And I'm just going to say, oops. Just, it reassures me that everything ran correctly. All right, and now basically I'm going to just start playing with data. Okay, so one thing, I'm going to use NumPy quite a bit, so I'm going to call NumPy, and I'm going to say NumPy set, I'm going to set some parameters, so print options. And I just want to show that sometimes I want to have a certain degree of precision, so I don't want to have that many decimal points. So I'm just going to say precision equal to. And I can just write a little comment here and just say decimal precision. All right, so I'm going to go ahead and test this just to make sure everything is running. Control X, Y, enter. And now I'm in the environment, so I'm just going to type Python example, and that's basically all you have to do. So everything still runs the same, except that now we are, I think for the first time, adding, instead of sklearn or pandas, we're using the NumPy and TensorFlow libraries. I'm going to run that. And there you go. It ran. So you can see it got to the print done. So that tells me there were no errors. And so that's a good thing. All right. So whenever you're dealing now, okay. So one important thing I should say is I wish I could get rid of this blue thing here. I don't know why. If anyone knows, please let me know. All right. So why is TensorFlow called TensorFlow? Who can tell me that? Why is TensorFlow called TensorFlow? What does the name mean? Maybe those of you that already took 530, what does TensorFlow stand for? Thanks. Thank you. That was helpful. So TensorFlow means flow of tensors. Okay, flow of tensors. So imagine a graph, like some kind of a graph, like a network, like you guys taking some networking classes. So like routers and switches and computers, right? It's a network. So that's a graph. Right? It's a graph of data flowing through the different nodes, through the links and the devices. Where you have nodes, as I said, you have two types of things, either data or operations. Like if I have a data A and a data B and I want to multiply them, I have a node A, node B, and a node C, which is the multiplication of those two inputs, and then I get an output. So that's what the name means. It means the flow of data through a network, right? In this particular case, a graph. And so the word flow comes from that. Tensor just means data, okay? Data. In the context of mathematics, the term tensor has a specific meaning, right? And it just means, you know, data can be represented in, you know, we know about variables, right? And whenever we talk about a variable, we know we just have one value in there. But you guys learn arrays, right? You guys learn, for instance, a one-dimensional array is just an array of indices, let's say from 0 to 10. So in that case, that variable now has 10 values in it. And so the correct name in mathematics for that is a set of values. It's no longer just a value of one, but it's a set of values that have a specific order, right? And that is in math, that's called a vector, okay? If you just have one single value, then it's called, in linear algebra, it's called a scalar. Now, we learn in programming about two-dimensional arrays, right? You guys have done two-dimensional arrays, you know, where we have the two for loops and the I and the J and everything. And those are called two-dimensional arrays or a matrix, right? So matrices is the proper term for that one. Now, you've all played with a Rubik's Cube, right? And that's a cube. It has how many dimensions? It has 3 dimensions, you know, I, J, and Z or K, right? And that's called a cube. And now, you know, we go from a vector to a matrix to a cube, for instance, right? In our data. And then what if we wanted to represent data with more? So you could build, I don't know if you've ever done this, I'm sure you did in one of your classes, but you can build a data structure that is not a one-dimensional array or two-dimensional array or even a three-dimensional array, but a four-dimensional array. That also works. It would just be what is called a hypercube, right? It's gonna be 4 dimensions and 5 dimensions and 6, you know, and so on. There's no limit. But all of those hold data, right? So the vector, you have no doubt that it just holds data, right? And you can see that if I create a list, for instance, in Python, right, that's gonna be, you know, 1, 2, 4, 6, and so on, right? That is a one-dimensional array or a vector in math. So what do all of these things have in common? A scalar, a vector, a matrix, a cube, a hypercube? They have in common that they can all be referred to as a tensor, okay? So the tensor word is the general name for all of those things. And so that's what TensorFlow is. It's a flow of data that can be a scalar, a vector, a matrix, a cube, a hypercube, and so on, okay? So the tensor word kind of refers to the data itself and the implication of the operation. So for instance, whenever we want to navigate through the data now, you know, let's say it's a two-dimensional array or a matrix, we're no longer going to use 2 for loops, I and J. That is the most inefficient way to process and get that data. Instead, we have to learn how to process the data as a matrix, right? And take advantage of the math operations that are optimal for that. And that is why we need something like TensorFlow or NumPy. These are libraries that are highly efficient for doing these kinds of operations. All right, so now that I've said that, then let's get started and let's just, you know, let's just play. Let's play with some of these, these ideas, okay? Remember, again, I will do at some point a formal introduction to NumPy. And today I'm just really we're just getting into the water slowly, okay? So let's think about the classic problem. What is the classic problem in machine learning? This is gonna be supervised learning again. What do I have? I have data, right? What are the names of the 2 variables that I have? X and Y. X is the data, Y are the labels. All right, let's start there. x equal y equal. Same thing we've done before, right? You know, it hasn't changed. So we're just kind of doing it in another way, but now excuse me. What I do want to emphasize, remember, we are now in the big data realm. So things have to be in parallel. All right, so that means NumPy. So let's start with NumPy. So NumPy, as you can see, import NumPy as NP. I'm going to create a simple vector, okay? Now in NumPy, you use the NumPy array. Remember that I want to distinguish between x equal this, that is a Python list, versus x np.array, which is it's no longer a list, okay? It is an actual array, and specifically a NumPy array. So that's a very important distinction. Now you can still use lists for some things, and we will use them, but usually whenever we're dealing with our x and our y, our data, we will be using the NumPy array now, or as tensors. The great thing about TensorFlow 2 that I do actually really like is that you can go from one to the other easily. So you can now go from a tensor to a NumPy array and back very easily, and that's really great. NumPy was always very well done. TensorFlow was a little bit sloppy initially, a little bit messy, still great, just a little bit sloppy, but they're trying to make it a lot more consistent with NumPy, more intuitive, certainly. All right, so I'm going to create a NumPy array. So the way that I do it is I'm going to plug in a list in here, and the list will be typecasted or converted into a NumPy array. So I'm going to say, you know, some values, 5, 4, 3, 2, 1, right? And then also one other thing about everything that we're doing now, TensorFlow in particular, it's very verbose. And what that means is that you have a lot of like parameters and things are now very wordy. So you can see I'm going to specify data type, and that just means I want this to be a NumPy array of type integer, an int32. Because remember that the underlying thing is C and C++, right? Remember when we took 450, we discussed that in C, and I'm sure you in other classes that there's a lot of data types in C, C++, int32, int64, you know, and so on. So you can define the data sizes, and this is actually very important sometimes. All right, now that I've done this, I'm also going to create the labels. Now in the labels, you know, I'm just going to make a list. So I'm going to say 1, 2, 3, 4, 5, just some values. I really don't care the logic right now. Now I want to differentiate though that this is a list and not a NumPy array. So they are different objects, and you must understand that. However, now I want a NumPy array to be a tensor. This used to be bit of work before. And now it's pretty straightforward. I'm just going to create a new variable. I like to put that whenever whenever something is a tensor, I like to do that, you know, x_tf. That's just style. You don't have to do it. I mean, you'll develop your own style. For me, it's just something I like to do. All right, and now I'm going to make for the first time a call to TensorFlow. I'm going to say tf dot convert to right. So I'm going to convert to tensor. And what am I going to convert to tensor? I'm just going to convert x. So remember, x is not a tensor yet in the sense that it's not a TensorFlow tensor, right? Whenever I say a tensor, I probably mean the object, the data type, the data structure, whatever you want to call it, in TensorFlow. Whenever I say a NumPy array, I mean the NumPy version, okay? So that's all I'm going to do right now. I'm going to convert it to a tensor. I want to see if it'll run, okay? So I'm gonna run it here. All right. So it ran, and no errors. It ran until done, so the code didn't error out. Don't worry about these CUDA error. That's just because I haven't done the fix that Mitch sent, but I'll do that later today. All right, so that is, the example. So now let's go back to the code. All right. So as you can see, I can't stress how amazing this is. Okay, this is an amazing thing that you guys are just lucky to have it now as you get started. This was not available before. Switching from one to the other wasn't so straightforward. All right, so now I'm also, notice that I applied it to a NumPy array. Now I'm going to apply that to a list. So I'm going to take YTF, and I'm going to say tf.convert to tensor, right? And what am I going to convert to a tensor? I'm going to convert the list. So notice just as well. Once I've done that, I'm going to just go ahead and print. And notice that now I'm going to try to print XTF. So that, oops. I'm going to try to print XTF, which basically means I am printing the tensor of the data 54321, which are all int, and which are now a tensor in the context of TensorFlow. I'm going to go ahead and run that. All right, and you can see it here. Now I want you to notice something. Look at that, what I just highlighted. It looks a little strange, doesn't it? You probably expected just to see, maybe in square brackets, a 5, 4, 3, 2, 1, and that was it. But I didn't print a NumPy array or just a list or a vector. I printed a tensor. And what TensorFlow does by default is that when it prints like this, it gives you basically, it tells you that it's a tensor. It gives you the data, which this wasn't there before. This was a great thing that they added. It gives you the shape, because remember, now these are shapes. Now remember, this shape means what? How many, so if you look at this, it tells you that you have 5 rows, okay? So, or it's a list of 5, okay? And then here it gives you the data type. As we start doing more complex tensors, we're gonna see 2-dimensional, 3-dimensional things, 4-dimensional things, and there's a lot. There's a lot, there's a lot to learn with TensorFlow. So certainly, but shape is essential. It's an essential component of understanding, because again, it kind of goes back to the idea of linear algebra. So that whole idea, now you don't need all of linear algebra for this course. You don't need it. In fact, I mean, it's not required, but it is helpful to have a sense of how it works. Okay, so there are some concepts in linear algebra that translate really well to deep learning, and TensorFlow in particular. So shapes of the data now, and those shapes determine how we perform operations. All right. So let's, as I said, we're just, playing with this data. So let's try something else. I'm going to now create a matrix of all ones. Okay, so I'm going to create a matrix, which means a 2-dimensional array of all ones. I want it to be a tensor, so I'm going to just, so I know, I'm going to put that tensor TF there. Oops. And then I'm going to say, I want it to be an all ones tensor. So guess what? TensorFlow has a way to do that. And you just do tf.ones. Okay, that's a function in TensorFlow that allows you to create a 2-dimensional matrix. Now you need to specify the shape of it. Okay, so that's the next thing. So the shape of this one, I want it to be 2 rows and 3 columns. Okay, so now, that's the matrix that I'm creating. Okay, so then I'm going to go ahead over here, and again, I'm going to print it. So I'm going to say print ones underscore TF. Okay, so I'm going to try this one now, and let's see what we get. All right, so I'm going to hit Control X, Y. Right. I can't stress sometimes this is the most important, right? Dealing with those data sets, because everything is data, so you kind of have to really understand. Now, don't get overwhelmed. It'll come to you slowly, and be ready that in 2 years they're going to change everything again. So you have to really keep up to date with this. But you can see the same thing. I printed the tensor. It's a TF tensor. You can see it's got 2 rows and 3 columns, and the values in it are all ones. Okay, the shape is 2 by 3, and it's a float 32 data. Are there any questions so far, guys? No questions? Pretty easy. Okay. So now, what if you don't want to print all that whole TF tensor, and you really just want to print the data? What can you do then? Well, as it turns out, now TensorFlow 2 also has something for that. So now we're going to do print, right? Print, and let's just say look at just the values of the tensor. You don't care about the sizes. Also, you want to be able now to manipulate this, right? You want to be able to just manipulate the data, maybe slice it, etc. So look at values of a tensor. Look at just the values of a tensor. So let's go ahead. And the way we can do this is, now I'm going to do a print. But notice, I want to see the values of ones underscore TF, right? So I'm going to take ones underscore TF, which is currently a tensor in TensorFlow, and I'm just going to convert it to a NumPy array. And when I convert something to a NumPy array, I can just treat it now like as a NumPy array and manipulate it and everything. All right, so I'm going to do that one. Control X, Y. I'm going to run it. And you can see that whereas before the tensor looks like that, the NumPy array only looks like that, right? So I can just deal with the data now instead of the actual object. Okay. All right. So just pretty simple stuff, but extremely important. This will help you a lot when you're debugging things, when you're solving a problem and you're dealing with the data. Now, something you have to do a lot of the time is you have to do typecasting. So you have to convert something between one data type and another data type. So let's take our XTF that we had before, which is a tensor, and let's just say print cast data type. And now what I'm going to do is I'm going to take XTF underscore, and this was int32, wasn't it? X was int32, you can see that there. And I'm going to convert it to int64. The dimensions now are very important. So I'm going to say 64. So what I'm going to do is I'm going to do tf.cast. tf.cast. And what am I going to cast? I'm going to cast XTF, and I'm going to cast it to the data type int64. All right. And now I can go ahead and actually print out the new data type for this one. So I'm just going to say x underscore tf underscore 64 dot, because it's a tensor, data type. Okay, so I'm going to print that out. And we are going to assess what that means. And you can see now that I printed cast data type, and now the new data type is int64 instead of int 32. Does that make sense, guys? Are there any questions so far? Okay, so let's keep going. All right, so let's keep going then. I'm going to now reopen the file. Now we're gonna, again, I'm not really today like introducing specific concepts. We're just really getting our hands dirty with TensorFlow 2. I'm going to now show an example of something that is extremely important in TensorFlow, and that is basically linear algebra maths, right? So linear algebra maths, which, you know, just the operations of it. So there's a lot of operations in linear algebra that you sometimes end up using. So this, you know, one of them is something called the transpose. Transpose. Without getting into too much detail of the transpose is necessary sometimes to perform matrix multiplications, okay, which are different than just regular multiplications. In fact, in TensorFlow and in NumPy, you will find two types of multiplication, what is called an element-wise, and I would recommend that if you have your notebook, take your notebook out and write this down. So there are in TensorFlow and in NumPy two types of multiplication. Because remember, you're no longer multiplying 3 times 4. You're now multiplying the set of 2, 3, 7, 17, 18 times a matrix that is, you know, 3, 7, 5, 7 in one row, 8, 7, 5 in another row. So you're making much more complex multiplications, but the advantage is that those multiplications are done in parallel. So you will understand why this is important, because, you know, what would take you days on a CPU will take you hours on a GPU. And so you gotta find those efficiencies. All right, so anyway, so as part of linear algebra maths, there's a lot of techniques out there. One of them is called the transpose. When I don't want to switch to the whiteboard right now, so eventually I'll get to describe this a little bit, but just think of it as a matrix that gets flipped. So imagine, for instance, that we have, imagine that you have a, imagine a door. That's a good analogy. We all know what a door looks like, right? The door is longer going up and down in the up and down sense and shorter in the left and right sense. Imagine that's a data set of rows and columns, right? A transpose is kind of like taking that door, which is kind of right now sitting as we always see it, and moving it 90 degrees. That's sort of a good understanding of it right now. We're going to rotate it 90 degrees so that now the longer part is in the left and to right sense, and the shorter part is in the up and down sense. Just think of it that way, okay? Don't worry so much about anything else. And that's really all we're going to do, is that if we have a data set, now there are reasons why we want to do this sometimes, and you know, that will become more apparent later. But for now, let's just think of the mechanics of that, right? So how would we perform that? Well, it just so happens that TensorFlow excels at this. It has a lot of functions to perform these types of operations. So let's see an example of that. So I'm going to use the letter M to indicate matrix. And now I'm going to say matrix is equal to TF dot. Now I want a data set. But I no longer, I don't want to always like have to type all the values because that would be a lot of work. So what you usually do, and in fact, do you guys remember that I said that when you were in gradient descent, when you were going through those values, you were the giant. Remember that I said you must start in multiple locations, right? You can't, because otherwise you end up in a local minimum instead of the global minimum. So if you remember that concept, I said you kind of want to do that randomly. And so what ends up happening is that you initialize things like this matrix M, sort of like that. You initialize them with specific what are called distributions, either randomly or a normal distribution with some parameters like you learn in your statistics class, like when you have a normal distribution and you have a mean and a standard deviation. Okay, so in this case, I'm going to take the simple random approach. So I'm just going to say random. So TF.random, but a random uniform distribution. And it just means the values are not entirely random, right? There's a specific pattern to them. So I'm going to initialize an object like that. Okay, you can see that here. It's going to be, so now it's going to be an object M that has data randomly selected uniform. And what's the other thing I need to define for this? If it's a matrix, what do I need to define for it additionally? You guys still there? You need to define the shape, right? So we're going to define the shape of the matrix. So I'm going to say shape 5, 10. Okay? And so what does that mean? It means that now I have 5 by 10. So tell me, how many samples do I have in this data set, M? 50. I do not have 50. I have 50 values. I don't have 50 samples. Remember those key terms, right? What is a sample? If the shape is 5 by 10, how many samples do I have? Assuming M is a data set, right? We just described this a few minutes ago in the previous lecture. How many samples?
5.
5. Very good. Per sample, because we have 5 rows, per sample, how many features do we have? How many features?
10.
10. Every sample, every column, remember, again, I stress this. 5 is the rows, samples, 10 is the columns, features, okay? So don't forget that. All right, so I created M, and now I'm going to apply this so-called transpose. So I'm going to say M transpose. Remember, that's the door analogy. For now, we're just looking at the mechanics. So M transpose will be equal to TF dot like that. Pretty intuitive, actually, the way that they've written it. And now you plug in here M. You see that? So that just means that we're flipping the door, okay? So the door now has been flipped. So now if you print, now we're gonna print the object. I'm gonna do print over here, and I'm gonna say, you know what? First of all, I'm gonna print M.shape, the original, right? 5 by 10, comma, and then I'm gonna say, transposes, that's a word, 2. And then I'm going to say the shape of the other one, which is M underscore transpose underscore, or not underscore. Yeah, no, dot shape. All right, so now I'm going to print the shapes of both of these objects. So let's take a look at what happens. Oops, no, that's not what I want. All right. What happened? You can see here we printed linear algebra math transpose, and now the object was 5 by 10, and guess what? Now it is 10 by 5. You see how we kind of translated that? It's almost like we take, there's a definition for a transpose, and the definition of a transpose is that you take the original data and all the rows become the columns of the next data. So if you look, it's like I grabbed the top row and it became the first column. Then I grabbed the next row and it became the second column. Then I grabbed the third row and it became the third column, and so forth. Okay, so that's kind of how it works. But you can see the shape there, and that really tells you what's going on. All right. So later on, don't worry so much right now of the intuition of this. Later on, I'll do a couple of operations, but there are very specific places where this is important. Transpose is used extensively in deep learning when we're mapping. It's a mapping function, right? We map from one space to another space, okay? And so that's an important concept. But we will come back to that when I'm on the whiteboard. All right. Are there any questions so far? Okay, no questions, it seems. So let's go back to the code. Another thing you're going to have to do in machine learning, deep learning, is you're going to have to reshape objects. What's one good example of when you will have to definitely reshape things? And what I mean by reshape is that something has a specific dimension and you convert it to another dimension. So let me give you an example of that. Let's say that I create now n, and n is going to be, again, tf.1s. There's also tf0s, but let's try 1s. And I'm going to say that I want this to be just a vector of size 20. So I'm going to say 20, comma. That's the notation of how you do it. All right, it expects a tuple. That's the problem. All right, so you do this. And then now I'm going to make this vector, basically, or a one-dimensional array. I'm going to turn it into a two-dimensional. All right, so I'm going to do tf.reshape. And then after reshape, what do I reshape? N. N, right? So I'm reshaping N. And I need to specify, as you might imagine, the shape. Right? So that's, kind of where you want to be. So I want to reshape it into a two-dimensional. So if I have something that's 20, of course, it has to be something that will fit, right? So for instance, I can make something that has 20 values into a 2 by 10, or I can make it into a 4 by 5, right? So 4 by 5. Why do I have? Okay. 4 by 5. So what does that mean? It means that I have 4 rows and 5 columns, okay? So I have enough values to convert a one-dimensional into a two-dimensional. Okay, and you can do it the other way around. You can have a two-dimensional thing and convert it into a one-dimensional as well. You can, you can do lots of things with this. So this is only like, as they say, the tip of the iceberg. There's a lot more. And you will, as you start working through algorithms and problems, you know, you'll come across the variance. So now let's print out the shape. So I'm going to say 2D, excuse me, and 2D dot shape. All right, so let's run this one. And you can see that I converted the one-dimensional into a two-dimensional array. All right, so what's an example of, let's say that we wanted to do backwards. We have a two-dimensional array, and we kind of wanted to make it a one-dimensional array. Can you guys think of a reason why you would want to do that? What's one example of something that might require you to do that? What do you guys think? No ideas? You know, imagine, we haven't gotten to images yet, but we will soon, probably next Tuesday or Monday, sorry, we will look at image processing. What usually a grayscale image, an image that is just black and white, is two-dimensional. But sometimes what you want to do is you want to stretch it, right? So let's say that I have a 4x5, you know, then you stretch it into a vector. So the example of that is MNIS, right? So MNIS is 28 by 28, but that can be stretched into what? 784. Usually it's very easy to do that. You don't need, sometimes we have things, little tricks that we can do in the shape, like putting in a -1. So instead of a 4, I can sometimes just put a -1. And when I put a -1 there where the 4 would be, it's basically telling TensorFlow to figure out, okay, you know what? Figure out the dimension yourself. This is the value. Just, I want a one-dimensional, and you figure out the numbers, right? So you can do that as well. All right. Are there any questions so far? Wow, no questions. Okay. So let's look at another scenario. And this one is a little bit difficult to understand sometimes, the reasoning for it. So remember, right now, I'm showing you the mechanics of things, but you might say, why would you ever need something like that? So let's take a look at this example. I'm going to create another one, and I'm going to call it TF zeros. And I'm going to do, you know, zeros. I'm going to give it specific values, or no, sorry, not values, dimensions. And this one will have more dimensions. It's going to have one dimension of 1, then a dimension of 3, then a dimension of 1, then a dimension of 5, then a dimension of 1. So this is, technically speaking, it's a hypercube, right? It's got 5 dimensions, even though a lot of them just contain the one thing. So it's similar to saying I have a vector. So a vector is a vector of 5 values. So that's 1 by 5, right? Or I have a vector of matrices. So I have 1 by 4 by 5. Right? So you can basically create a vector of matrices, or, you know, just like a vector. So this is just a hypercube where, you know, you have elements, you know, of all of this in just that one thing. Okay? So why do you use something like this? The reason why you use something like this is that when you perform a matrix multiplication, you might have a data set. Let's say that you have a data set of 5. Imagine you have like a building of 5 stories, right? A building of 5 stories. But you really just want to apply the matrix multiplication to stories 2 and 4. and you kind of want to skip stories 1, 3, and 5. You see that? So that's kind of sort of an analogy of why you would do that in a very exaggerated way, that you do this because sometimes you perform matrix multiplications and you really just want to align certain things to the rows or columns of another matrix. Let's call it P1 and P2, and want to perform an operation between P1 and P2. So basically what this is called is sometimes you're folding and unfolding a matrix. Okay, you're adding dimensions or you're removing dimensions, which is sometimes called squeezing. All right, so for instance, let's say I want, I perform my operation, I no longer need it to be of these dimensions, so now what am I going to do? I'm going to remove them. So I'm going to do, let's say, print first. I'm going to do a print, and I'm going to do p dot shape. All right, so let's run that one. Okay. You can see the dimension of this is, the one that I showed you. It looks like that, okay? It looks like that. We can also go back to the code. And I can actually do print, and I'm gonna print P itself. All right, so now I'm gonna repeat this operation. And you can see it shows the tensor now, right? And it basically shows you how the data looks. And the thing that might be confusing to you is that now you have all these square brackets. And this is a little bit difficult to interpret. What I would recommend is I would strongly say that you should copy this, copy that out into your own environment somewhere and play with it. Figure out that it is in fact like a 5-dimensional Rubik's Cube, but some dimensions are just ones, okay? And other dimensions have more. You can see that here as well. Here is in the shape, but what I like about this is that it shows this. The square brackets kind of, hold the dimensions in there. All right, as I said, this would be because what you wanted to align this vector, that is 3 by 5 with something. All right, so now how do I, sometimes after you've performed an operation between tensors, you want to actually remove that those dimensions because you don't need them anymore. So as I said, this is something that is very common in deep learning. As you start to get really advanced in things and you perform these matrix multiplications, sometimes you need to add dimensions and sometimes you need to remove the dimensions because matrices will have different shapes. This will become more obvious as we start doing problems, but that's why it's important that we start here, with tensors and tensor operations. All right, so now what we want to do is, still have a few minutes, so we want to remove these dimensions. Let's say that we no longer need to perform the multiplications, we just need the vector, 3 by 5, the data there back. So now what I can do is, I'm going to use the squeeze method in TensorFlow, which this was taken from NumPy. NumPy had it, and then they adapted it. So it's called squeezed, right? And it's basically the function that allows you to remove those things. I'm going to do tf dot squeeze. And what am I going to squeeze? I'm going to squeeze P. And I'm also going, I'm going to say that I want to remove I want to remove not all the ones. If you just do it by default, it'll remove all ones. So basically the definition of this function, if you look it up in TensorFlow, is that squeeze basically takes a matrix, any dimension that's a 1 gets removed. But in this case, I actually want to be more specific about it, and I'm going to say axis equal, and then I'm going to say as a list, I'm going to indicate, okay, I want you to remove dimension 2, because this is 0, this is 1, so this one should be 2, and this is 3, and this one is 4. So I want to remove those. So I'm going to say 2, 4. Okay, and then over here, I'm just going to add a little comment. I'm going to say remove 1 dimensions on these axes. All right, so I'm going to do that. And now I'm going to print out the shape of squeeze, P squeeze. So I'm going to say print P underscore squeezed dot shape. Okay, so I'm going to do that one. All right, let's try it out, see what happens. So now run it. And if you look, the dimensions now are 1, 3, 5. So it's the 1 here stayed, this 3 stayed, this 1 disappeared, the 5 stayed, and the 1 stayed. Remember, no data was lost because you can take, you know, a vector, right, and just make it 2-dimensional, maybe add another dimension, but you still don't lose the data. Okay, and so the data is still there. It's just that the hypercube now became a cube. Or maybe you had a 2-dimensional array and it became a 1-dimension. But the dimensions change, not the vector. Certainly, playing with this, I think, will help you a little bit to visualize that. Are there any questions so far? All right, I'm almost done with this example, so I really just want to finish it. All right, so I'm actually really doing well in time. So let's just do the last one, which will be, I'm going to create now a matrix, right? So remember what I said. Remember the giant, right, in gradient descent. The giant needs to start in different positions. So to do that, I want to initialize my matrices with different values. So in this case, I'm going to initialize a matrix, TF, and I'm going to say TF dot random uniform, which is the one I had used before, random uniform. And then I'm going to initialize it to have, it's going to have the shape of, let's say 5, 2. 5, 2. And now, but now notice, I'm going to provide additional parameters. I'm going to say, yeah, I want it to be random uniform, but within a range. So min value will be minus 1.0. And then max value, or max val, will be 1.0. Okay? So now I can create this matrix to be of specific sizes. I can also print it. So I'm going to say print matrix 1 underscore TF. I'm going to run that. And you can see that there. Now I have my 5x2 matrix with all values which are random, but they are within -1 and 1. You see that? So I have a little bit more control of what I wanted in my data. So that's extremely powerful, but because this is how you control, you know, where the giant starts in that search for the optimal. The last thing I will show, and then we'll stop here for today, is what if you wanted to use a normal distribution? And so then let's create another one, matrix 2 TF equal TF dot, and now I'm going to say random, still random, figure out the numbers, but with a normal distribution, just like you learned in your statistics class, right? And then we're going to say, still need to specify the shape. Use the same one. Oops. 5, 2. But then also here, now I need to specify that I want a mean, which is going to be 0.0. And I want a standard deviation that is going to be 1.0. Like that. All right, you can see that there. And then finally, I'm going to print this out. That's going to be matrix underscore TF. Oh, matrix 2, sorry. Matrix 2. So now I'm going to save it, run it again. And you can see that there. Here we have one tensor. They both have the same dimensions. But this one follows a uniform random with -1, 1 values. And this is a normal distribution. And it's got a mean of 0 and a standard deviation of 1. All right, that concludes the first example of TensorFlow 2. So hopefully you're excited. You know, you're learning something really amazing here. Next week, I will continue with TensorFlow 2 examples. I think that's where I use the images, so I'll do that one. That's a little bit more elaborate. That'll probably be just the first hour and a half. And then don't forget the second hour and a half, your exam. I'll post it at that time. And, you know, and then also the Twitter practical exam will begin, and you'll have a week for that one. All right. Also, don't forget to do what Mitch said on his email. I'm sure all the instructions are there, and then, or I think there was a video, so also look at that. All right, and that's just to update so that we have the GPUs all the time. All right, so that concludes class for today. I'm going to, yeah, so are there any questions, I guess? I'll stay for a couple of minutes for questions. If not, we'll stop here, and I will see you guys next Monday.